This is an example of how we can use polar form to solve or prove trigonometric identities, and we're also going to use some facts about complex numbers and the binomial theorem. So putting together several strategies here. And these strategies will be useful in other problems as well, where we're looking at either the real or the imaginary part of a complex number. So this is what we're supposed to show. Left-hand side equals the right-hand side. Right-hand side looks like a big mess of powers of cosine. So that indicates to me that perhaps we're doing something related to the binomial theorem. And I can also see some big number coefficients here, which also suggest some binomial coefficients. But I notice I only have the odd powers of cosine, so something else must be happening here as well. The key here is we need to incorporate complex numbers somehow, and right now we just have cosines, which are usually the real part in polar form. So what we're going to do is we're going to start with the entire polar form. Instead of cosine 7 theta, we're going to take cis 7 theta. We're going to do that because we have a theorem, Demoivre's theorem, which says that we can take that multiple out, and this is equivalent to whatever cis theta is to the 7th power. But now cis theta to the 7th power, that means cosine theta plus I sine theta to the 7th. And notice now we have our binomial. We have two terms and we're going to expand this. So back up here, remember our binomial theorem. Well, you don't have to remember it, right? Because it's in your formula packet. All right, so in this case, our first term is cosine. Our second term is I times sine. So we're going to have, let's see, 7 choose 0. That's going to be 1 cosine to the 7th. Here we go. Then we're going to take 7 choose 1, that's 7, cosine to the 6th, and now we have a power of I. And we'll continue down our coefficients here. Give myself Pascal's triangle to help us out. Or if it were calculator paper, you could use that, or the formula to calculate the coefficients. What? But not like that. Ooh. Try that again. Here's row 3, row 4, row 5, row 6, and row 7, and I know it's going to be symmetric, so I just need to get first grouping. Okay, so there's our 1, our 7, 21, cosines now to the 5th power. I sine theta is squared. And I'm just going to continue all of my terms here. We have 21, 35. Cosines now to the 4th power. I sine is to the 3rd. Another 35. Ooh, you get to delight in smartboard antics here, even though you're not here in person. Isn't that nice? Okay, 21, square. Almost there. So we can sneak in our sine of the 7th there. Okay, so let's take a look at what we have here. We have a whole bunch of powers in cosine and sine, but some terms are going to be real and some are going to be imaginary. And I'm going to pick out which ones those are. So I see obviously this has no I in it. Next term does have an I. Third term has an I, but it's going to be squared, turning it into a real number. And the same thing's going to happen with all the even powers of sine, which gives us 4 terms in this expansion that are now real numbers. And because we were interested initially, we wanted to find about cosine of 7 theta, but that is the real part of cis 7 theta. Use cosine 7 theta plus I sine 7 theta. So remember, a strategy we had way back before polar form was that when we were dealing with complex numbers, we can set the real parts equal to each other, and we can set the imaginary parts equal to each other when we have equal complex numbers. There's no way that we're going to get an imaginary number from a real number using just simple adding, subtracting, and multiplying and dividing. Which means that my cosine then is just the sum of those 4 terms. And now here, my I squared is going to turn into a minus 1, so I'll go ahead and change that plus 21 to a minus. My word. Or will I? Yes, I will. Okay. And here we have to the 4th, so that will stay positive. Our sine is now to the 4th, plus our last term, 7 cosine theta. I to the 6th is again going to be minus, so change that plus to a minus. Okay, and now you'll say, but Ms. Doring, that what we were trying to prove only had cosines in it. That's okay though, because now we can easily translate between cosine and sine using the fact that sine squared is 1 minus cosine squared. Substituting that in and rearranging, that part is familiar, we can do that. So the big thing that I wanted to emphasize here is that you can set real equal to real and imaginary equal to imaginary. But sometimes you have to start with the whole thing in order to get just the real or imaginary part.